Right now, there is a single quiet fact about the place you inhabit, one almost never stated directly, one almost never taught in any classroom. And yet, it governs every photograph of the night sky you have ever seen, every trajectory every spacecraft has ever flown, and every mental map of the cosmos you have ever built. Our solar system is not a sphere. It is not a loose cloud of bodies drifting in all directions around a central star. It is a disk, a wide, slowly turning, almost impossibly thin disk of planets and moons and asteroids and comets, all sweeping through the same gentle plane, all bending around the same burning hub, all carried along by the same sideways motion that has held them in place for 4.5 billion years. The flatness is real. The vertical axis, the direction straight up above the sun, straight down below it, is a direction in which almost nothing in our experience has ever traveled. If you enjoy journeys that quietly reshape the way you see the universe, do me a small favor and hit the like button and subscribe. It genuinely helps this channel reach others who would find their way here. Thank you for being present tonight. But for the next several hours, none of what waits beyond this room needs your attention. Let your shoulders settle. Let the day release its hold. Let your breathing find its own pace. Let's begin. The flatness of the solar system is the most consequential geometric fact about where you live. It is also among the most overlooked because nearly every diagram you have ever seen of the planetary system has been drawn either from the side where the disk appears obvious and unremarkable, or from directly above, where the flatness is simply assumed and never interrogated. No one pauses to ask why everything orbits in the same plane. The plane is just presented as the backdrop, the given, the starting point, but it is not a given. It is a conclusion, the outcome of a very specific chain of physical events that unfolded long before the sun ignited, long before a single planet assembled itself from dust, long before any surface existed anywhere in the solar system on which something might one day look upward and wonder what it was looking at. Standing on Earth today, the disk is everywhere around you, though you may not have named it as such. The sun rises and sets along a particular arc across the sky. The moon follows that same arc. The planets, every one of them visible to the naked eye, drift along the same imaginary curve traced overhead night after night, year after year. Even without knowing its name, you have traced this line with your eyes countless times. Astronomers call it the ecliptic. It is the plane of Earth's orbit around the sun, projected outward as a line across the sphere of the sky. And because every major body in the solar system orbits within a few degrees of that same plane, the ecliptic is not merely Earth's orbital path. It is the signature of the disk itself, written across the night in the wandering lights of the planets. The flatness is not accidental. It is not a design choice. It is the fossil record of how everything here began. Imagine a vast, slowly rotating cloud of gas and dust, drifting through interstellar space wider across than any planetary system, thin and cold and dark, turning gently on its own axis as it drifts. Gravity inside the cloud pulls inward from every direction, but rotation resists collapse in one direction while permitting it freely in another. Along the spin axis, the direction you might think of as the cloud's north and south poles, nothing pushes back against gravity. The cloud collapses freely along that axis. Across the equatorial plane, however, the rotational motion of the cloud holds the material outward, and the cloud cannot collapse in that direction without first surrendering the spin that keeps it spread out. It takes an enormous amount of time and energy to shed that spin. The cloud is therefore not symmetric in how it falls. It collapses quickly from pole to pole and resists collapsing across its middle. What was a sphere becomes an oblate shape. What was an oblate shape becomes a disk. A young star ignites at the center, consuming the greatest portion of the infalling material. Around it, the remaining gas and dust settle into a broad rotating sheet. The protoplanetary disk, still warm from the energy of collapse, threaded through with magnetic fields, stirred by turbulence, slowly cooling toward the outer edges. In this disk, solid grains condense from the gas as temperature drops. The grains collide, they stick, the clumps grow. The growing bodies sweep up more material along their orbital paths, and over millions of years, Planets accumulate in the plane of the disk, inheriting exactly and precisely the geometry in which they formed. Any material that wanders too far above or below this plane is either dragged back by the disk's collective gravity, scattered outward and lost, or simply fails to grow into anything large. The plane is not merely where things happen to be. It is where things are permitted to assemble. This same sequence repeats itself wherever gravity and rotation are found together. The rings of Saturn are a small disk, formed by the same physics at a smaller scale. The Milky Way is a vast disk, flattened by billions of years of the same process, acting on hundreds of billions of stars. The accretion disks that spiral material onto black holes at the centers of distant galaxies are disks as well, collapsing, flattening, spinning, held open by the rotation they cannot shed. Flatness is what the universe almost always produces when gravity and rotation work together over long periods of time. A spherical solar system would be the strange thing. A disk is the natural outcome, the rule, not the exception. The plane the planet settled into has a precise technical definition. It is called the invariable plane, and it is calculated as the weighted average of all the planetary orbits, each orbit weighted by the angular momentum of the body following it. The planet contributing the most angular momentum exerts the strongest pull on where the invariable plane lies, and because Jupiter is by far the most massive planet in the solar system, its orbit dominates the calculation. Earth's own orbital plane, the ecliptic, tilts by only about 1.5 degrees relative to the invariable plane. For nearly all practical purposes, these two planes are the same thing, and the ecliptic is treated as synonymous with the plane of the solar system in most discussions. The other planets orbit within modest angles of this reference plane. Mercury, the innermost, sits at roughly 7 degrees, the steepest tilt among the 8 major planets. Venus, Mars, and the gas giant all orbit at smaller inclination. Pluto, the famous outlier, tilts at about 17 degrees, enough to give its elongated orbit a visible rise and fall above and below the disk. A handful of icy bodies in the distant outer system tilt more steeply still. Long-period comets, arriving from the distant reservoir that surrounds the solar system, can approach from nearly any direction, plunging through the disk at steep angles before swinging back into the dark. But these are ornaments on an essentially flat architecture. The bulk of the solar system's mass, its momentum, and its story all live within a thin band of space oriented to a single plane. The disk did not simply disappear when the planets finished forming. A diffuse residue of fine dust continues to populate the plane, replenished slowly by the ordinary processes of the solar system at work today. Collisions between asteroids in the belt between Mars and Jupiter grind rocky bodies into smaller bodies and eventually into microscopic grains. Comets shed material along their orbits as they pass close to the Sun, and volatiles boil away from their surfaces. The slow erosion of icy objects far beyond Neptune adds a faint contribution at the outer edges. All of this dust inherits the plane because everything that produces it lives in the plane, and the combined gravity of the planets and the pressure of sunlight keep it there. The result is a thin, faintly luminous sheet of dust that marks the geometry of the solar system long after the original protoplanetary disk dispersed. On a sufficiently clear and dark night, truly dark, far from any city, this dust is visible to the unaided human eye. It appears as a soft, pale cone of faint light, angled upward from the horizon just after the last glow of sunset fades, or stretching upward from the horizon in the hour before dawn arrives. It is called the zodiacal light, named for the band of constellations that lie along the ecliptic, the zodiac through which this glow appears to pass. What you are seeing is sunlight scattered back toward your eye by the dust of the plane, not a glow in the atmosphere, not an aurora. The disk of the solar system itself, made faintly luminous by the sun behind it. To see the zodiacal light on a dark night is to see with your own eyes the geometry of where you live. The zodiacal cloud is densest close to the sun and thins with distance outward. It also thins sharply in the vertical direction, dropping off quickly above and below the plane. Looking outward along the plane, your line of sight passes through the accumulated depth of all that dust, all that scattered sunlight, all that local luminosity. Looking perpendicular to the plane directly above the sun's north pole, or directly below its south, your line of sight passes through almost none of it. The sky in those two directions is among the cleanest available from anywhere inside our own solar system. The disk that gives us our home is the same structure that crowds the rest of the sky. The vertical directions are the directions where the universe is least obscured, where the view reaches furthest with the least interference. The disk of the solar system is itself nested inside a far larger disk, the Milky Way. The galaxy is a slowly turning spiral several 100,000 light-years in diameter, containing several 100 billion stars along with enormous quantities of gas, dust, and dark matter, all flattened by the same gravitational and rotational physics that flattened the solar system, though on a scale and over a time scale almost beyond meaningful comparison. But here is something worth pausing on. The plane of the Milky Way and the plane of the solar system are not the same plane. They are tilted relative to one another by roughly 60 degrees. The Sun and its family of planets orbit the galactic center on their own private plane, oriented quite differently from the broad disk of the galaxy as a whole. This difference is imperceptible from inside the solar system on any practical human timescale, but it matters for what the sky looks like from a vantage point above the Sun. From Earth, the band of the Milky Way cuts across the night sky in the familiar way, a soft glowing river of light, crossing from horizon to horizon, richest toward the constellation Sagittarius, where the galactic center lies. From a position directly above the Sun's north pole, looking outward, that band would appear in an entirely different geometric orientation. It would rise at a steep angle across the sky, rather than crossing it gently. The familiar landmarks of the southern sky as seen from Earth, the bright bulge of the galactic center, the dark dust lanes threading through the stellar light, the soft brightness of the inner spiral arms, would all lie in different positions relative to the horizon you would use as a reference. The stars themselves would be the same stars. The sky would carry the same light, but its arrangement would be unfamiliar in a way that is difficult to fully imagine without actually standing somewhere unfamiliar enough to experience it. The Sun moves through the galaxy as well, drifting at roughly 200 kilometers per second, relative to the average motion of nearby stars, carrying its entire planetary system along on this patient journey through the galactic neighborhood. The direction of that drift, projected against the background of distant stars, points toward a region of sky in the constellation Hercules. Over the full history of the solar system, this motion has carried the Sun through an enormous volume of the galaxy, through quiet regions and denser ones, through the outskirts of spiral arms, and through the calmer spaces between them. Currently, the Sun drifts through a region of relatively low-density interstellar gas called the local interstellar cloud, which is itself embedded within an even larger and lower-density cavity called the local bubble. This larger cavity was carved by the explosions of massive nearby stars tens of millions of years ago, supernova blasts that swept the surrounding gas outward and left a thinned region through which the Sun is now passing. The walls of this larger bubble glow faintly in the soft X-ray part of the spectrum, and the direction below the Sun's south pole in galactic terms opens into one of the clearer sightlines through this cavity toward the wider universe beyond. You live, in other words, at the intersection of multiple overlapping flatnesses, the disk of the solar system, the disk of the Milky Way, the elongated remnant of an ancient supernova cavity. Multiple rotations, multiple collapses, multiple histories of flattening, laid down over different timescales and oriented at different angles, all overlapping in the region of space your star happens to be crossing at this particular moment in galactic time. The geometry of where you are is not arbitrary. It is the layered consequence of clouds collapsing, gravity organizing, rotation flattening, and time enforcing its preferences at every scale it operates on. The simplest single fact that makes the rest of tonight's exploration coherent is this: the solar system is flat, the disk is real, the vertical axis is real, and the entire history of human spaceflight has taken place entirely within that disk, carried along by the same sideways current every spacecraft inherited from the planet it departed. what lies above and below, what the sun's poles actually look like, what the shape of our local bubble actually is, what the disk itself looks like from outside its own plane, remains among the least observed territories in the entire solar system. That is where tonight is going. The most important fact about leaving Earth is one rarely stated plainly outside the rooms where mission trajectories are designed. And yet it determines nearly everything about how spacecraft move through the solar system, why they go where they go, why they take the paths they take, and why certain destinations that appear close on a map are in practice among the most difficult places in the entire solar system to reach. You are not standing still. The ground beneath you is moving not from any local disturbance, not from any tremor or shift, but because the entire planet is sweeping sideways around the sun at a speed that is genuinely difficult to feel only because it is so perfectly constant, so perfectly shared by every atom of the world around you. Earth's orbital velocity is approximately 30 kilometers per second. Every second that passes, the planet has carried itself 30 kilometers further along its path around the sun. Every minute, nearly 2,000 kilometers. Every hour, more than 100,000. You, the room around you, the building, the air outside, the oceans, the crust, the deep interior, the whole planetary system, all of it moves together at that same enormous sideways speed. The motion is invisible precisely because nothing around you moves relative to anything else. But it is real, and it matters enormously for everything that follows tonight. A rocket lifting from Earth's surface inherits every kilometer of that sideways motion the instant its wheels leave the ground. It does not need to build orbital speed around the sun from nothing. It already possesses 30 kilometers per second of sideways velocity around the sun simply by virtue of having existed on a launch pad. What it must add to reach orbit around Earth itself is approximately 8 kilometers per second of additional velocity relative to Earth's surface, enough to stop falling back down and begin continuously missing the ground in a curve. What it must add beyond that to escape Earth's gravity and travel toward the Moon, toward Mars, toward Jupiter, is more modest still, because the Sun's gravity is already governing the broad shape of those journeys. The spacecraft nudges its inherited orbit into a slightly different one, widening it or shrinking it, bending it toward a new destination. Nothing the spacecraft does cancels the 30 kilometers per second it was born with. Nothing it does returns it to a state of rest with respect to the sun. The sideways motion is permanent. It is structural. It is the foundation on which every trajectory ever flown has been built. This single inheritance is the reason almost every spacecraft in the entire history of human spaceflight has traveled more or less within the plane of the planets. And it is the reason almost nothing humanity has ever launched has moved in any meaningful way above or below that plane. To rise out of the ecliptic, a spacecraft does not merely need to climb, it needs to erase the 30 kilometers per second of sideways motion it was born with and replace it with an equivalent velocity pointing in an entirely different direction, perpendicular to the plane, upward or downward out of the disk. The disk is not a road, it is a current. Everything within it is being carried along by that current, and redirecting course out of the flow is incomparably more expensive than continuing within it. Mission designers use a precise term for the total maneuver capacity a spacecraft carries with its onboard propellant. They call it delta V, the change in velocity available to the vehicle over the course of its entire operational life. Delta V is the currency of the solar system. Every maneuver spends some of it. When it is gone, the spacecraft can no longer change course. It can only follow whatever trajectory physics dictates from that point onward. The size of a spacecraft's delta V budget depends on how much propellant it carries at launch and how efficiently its engines convert that propellant into thrust. Chemical rockets, the kind that have lifted nearly everything humanity has ever sent into space, refined over 7 decades of practical engineering, have particular efficiency limits that set hard ceilings on the delta V any single mission can carry. The numbers that follow are approximate, but they are accurate enough for what tonight requires. Reaching low Earth orbit from the surface costs roughly 9 to 10 kilometers per second of delta V. Most of that cost is paid during the early climb, fighting gravity and atmospheric drag, while building up the sideways speed needed to stay in orbit once above the atmosphere. Departing Earth orbit for the Moon costs another 3 to 4 kilometers per second beyond that. A trajectory to Mars, using the standard low-energy path launched during a favorable window, when the two planets are well positioned relative to each other, costs roughly 4 kilometers per second beyond Earth orbit. A transfer to Jupiter, with or without gravity assists along the way, costs approximately 6.5 kilometers per second. These are the familiar destinations. Their costs are entirely within the capability of modern rockets, provided the spacecraft is sized appropriately and the mission is planned with care. A trajectory that would actually leave the plane of the solar system that would point directly upward or downward, out of the ecliptic, into the empty sky, above or below the disk, requires erasing essentially all of Earth's sideways orbital motion and replacing it with equivalent motion in the perpendicular direction. The cost is approximately 30 kilometers per second of delta V from low Earth orbit. No chemical rocket ever built has delivered anything close to that figure to a single spacecraft destined for an interplanetary mission. The most capable interplanetary vehicles ever flown have carried total delta V budgets in the range of 15 to 20 kilometers per second across their entire operational lives, and most of that was spent slowing down to enter orbit around a destination or making trajectory corrections along the way. The direct vertical climb out of the plane is not merely out of reach. It is not a difficult target being narrowly missed. It is out of reach by a factor that makes the comparison almost absurd. Sit with the strangeness of this for a moment. Sending a spacecraft all the way to Pluto, past Jupiter, past Saturn, past Uranus and Neptune, to the outermost edge of the planetary system, 3 billion miles from Earth, costs less delta V than sending that same spacecraft directly upward, perpendicular to the plane, to a height no greater than Earth's own distance from the Sun. The empty sky immediately above the Sun is, in the only currency that matters for spaceflight, more remote than the frozen bodies at the rim of the planetary system. The reason for this counterintuitive ranking is geometry. To travel outward toward Pluto, a spacecraft adds a modest amount of velocity in the direction it is already moving, gently widening its orbit into a long, sweeping ellipse that carries it out past each successive planet in turn. The Sun's gravity does most of the actual work of the journey. The spacecraft provides only the initial push, and the orbit does the rest. The existing sideways motion is not wasted, it is the foundation of the trajectory. To travel upward, out of the plane, the spacecraft must push perpendicular to its existing motion. None of that existing motion helps. None of the Sun's gravity assists the climb, because the Sun's gravity points inward toward the Sun, not downward toward the plane. Every kilometer per second of vertical velocity must be purchased in full, with propellant burned in space, with no assist, no shortcut, no geometric leverage available. This is the underlying reason the polar regions of the Sun are, in the language of trajectory design, more remote than the outer planets, not because they are distant. The Sun's poles sit at exactly the same distance from Earth as the rest of the Sun, roughly 1 astronomical unit, approximately 150 million kilometers. They are difficult to reach for one reason only. Getting there means climbing out of the plane that gravity locked everything into 4.5 billion years ago. There is, however, a path around the delta V wall. It is a path that has made the entire history of outer solar system exploration possible, and it relies on a principle that turns the solar system's most massive bodies into something very close to a free propulsion system. When a spacecraft passes close to a planet, the planet's gravity curves the spacecraft's trajectory. If the geometry is chosen correctly, this deflection does not simply bend the path. It also changes the spacecraft's speed relative to the Sun. The planet, being unimaginably more massive, loses or gains a corresponding but infinitesimally small amount of orbital energy in exchange. The total energy of the system is conserved. The spacecraft borrows a fraction of the planet's orbital motion, and the planet loses an amount so tiny it could never be detected by any instrument. The maneuver is called a gravity assist, or a planetary flyby, or a swing bee. It is the closest equivalent to a free lunch that classical physics permits. A single well-designed flyby can change a spacecraft's velocity by several kilometers per second, depending on the planet's mass, the speed of the encounter, and the precise geometry of the approach. More massive planets offer larger assists. The angle at which the spacecraft skims past determines whether speed is added, subtracted, or redirected sideways, and it is the sideways redirections that matter most for changing orbital inclination. Jupiter is the most powerful gravitational slingshot in the solar system. A close flyby of Jupiter can change a spacecraft's velocity by 10 kilometers per second or more in a single pass. With the right approach geometry, Jupiter can redirect a spacecraft's trajectory sharply out of the plane, throwing it upward or downward relative to the ecliptic, for essentially no cost in propellant whatsoever. The cost instead is paid in trajectory design complexity and in mission duration. The spacecraft must arrive at Jupiter at exactly the right moment, along exactly the right approach path, to depart on exactly the desired trajectory. The window for such a launch is narrow, and once the trajectory is committed, it cannot be easily redrawn. Venus, smaller but far more conveniently located in the inner solar system, offers a different strategy. A single Venus flyby changes inclination only modestly, perhaps a few degrees. But a spacecraft that loops between an inner orbit and Venus repeatedly, with each pass tuned to add another small increment of orbital tilt, can accumulate inclination gradually across many years of patient maneuvering. No single flyby does the full work. The spacecraft pays in time rather than in propellant, climbing out of the plane one careful encounter at a time. There is a classical problem in orbital mechanics that captures precisely why moving between 2 points in the plane of the solar system is so much simpler than moving between a point in the plane and one above it. The problem asks, given a departure point, an arrival point, and a fixed travel time, what orbit connects them? Within the plane of the planets, where everything moves in roughly the same direction at broadly compatible speeds, this problem has elegant and practical solutions. The standard low-energy transfer orbit between any two planets, an ellipse that touches the orbit of the departure planet at one end and the orbit of the destination planet at the other, can be calculated straightforwardly, and the required maneuvers are well within chemical rocket capability. Leaving the plane makes the same problem severe. The connecting orbit now has to fight the geometry that makes every familiar shortcut unavailable. There is no need to dwell on the mathematics. The point is only this: the universe makes it easy to travel between bodies that share a plane, and hard to travel between a body in the plane and a point in empty space above it. The disk is generous to travelers moving within it. It is frugal with travelers who try to leave it. This is why mission planners, when comparing the difficulty of various destinations, rank the solar polar regions as harder than the icy edge of the planetary system. The icy edge is in the plane. The sun's poles are not. Getting to Pluto follows the flow of the current. Getting above the disk means swimming across it. Nothing forbids escape. No law of physics places the solar polar vantage permanently beyond reach. It simply costs more than any chemical rocket can pay in a single direct ascent. And the only path that has ever made it possible at all requires borrowing energy from the planets themselves, exchanging time and trajectory complexity for the delta V that no rocket can carry. Every spacecraft that has ever climbed meaningfully out of the plane has done so by using planets as stepping stones, patient, gravity-powered redirections that transform mission duration into inclination and years of flight time into the altitude above the disk that brute force could never afford. The plane is not a mistake. It is not a prison with locked doors. It is more precisely what it has always been, the natural consequence of how a solar system forms, holding on to its shape across billions of years. The current the disk carries everything along in has been running since before the first solid grain condensed from the cooling protoplanetary cloud. It will continue running long after anything alive today has ceased to exist. To go anywhere within that current is the work of an afternoon's worth of trajectory calculation and a few months of travel time. To step outside the current requires something different, a different kind of mission, a different kind of patience, a different way of thinking about what destinations are worth the cost. The polar regions of the sun have been waiting since the solar system formed. They will continue waiting. They are not going anywhere. What they hold, and what it means that we have barely visited them. That is the question the next part of tonight begins to answer. Almost everything humanity has ever learned about the Sun has been learned from its equator. The dark spots that drift across the visible disk in photographs taken from Earth. The bright flares that erupt and are captured on ultraviolet film. The slow rotation of magnetic structures across the face of the star. The luminous streamers of the corona revealed during the rare minutes of a total solar eclipse. The decades-long record of the 11-year activity cycle, charted by observatories on every continent. All of it, every frame of every image, every measurement from every instrument has been gathered from a vantage point within the plane of the planets. Looking at the Sun from the side, from the equatorial perspective, that is the only perspective our location has ever permitted. The poles of the Sun, the two regions where its rotation axis meets its outer surface, are largely invisible from Earth and from any spacecraft that has remained within the ecliptic. Even at the most favorable geometry, when Earth's slight orbital tilt brings one pole fractionally more into view, the polar regions are seen at a shallow grazing angle, compressed by foreshortening, most of their detail lost in the projection across the curved face of the star. To observe the poles with any real clarity requires a vantage point above or below the Sun, a position that, for the vast majority of the history of solar physics, has simply not been available. This matters more than it might initially seem. The poles are not quiet backwaters. They are not peripheral regions that can be safely ignored while the interesting science happens elsewhere. They are where some of the most consequential solar behavior originates. They are where the fastest component of the solar wind is born. They are where the Sun's global magnetic field reverses direction every 11 years. They are where the long-term memory of the solar cycle appears to reside, the mechanism by which the Sun carries information about one cycle forward into the next. Much of what appears at the equator as visible solar activity is the downstream consequence of processes that begin, accumulate, and resolve at the poles. To study the equator while missing the poles is to study the symptoms while the source goes unexamined. The concept that opens any serious discussion of the polar Sun is the coronal hole. The Sun's outer atmosphere, the corona, is a region of extraordinarily hot, thin, magnetized plasma extending outward from the visible surface for millions of kilometers. Within the corona, magnetic field lines generally form closed loops, arching upward from one point on the surface and curving back down to another, trapping the plasma within them. These closed-loop structures are the bright, complex features visible during total eclipses and in ultraviolet images of the Sun, the luminous architecture of the active corona. But in certain regions, the magnetic field lines do not close. Instead of looping back to the surface, they open outward into space, extending away from the Sun along trajectories that never return. In these regions, the coronal plasma is free to escape. Nothing holds it back. It flows outward along the open field lines and joins the continuous stream of charged particles pouring away from the Sun in every direction the solar wind. These open field regions appear dark in ultraviolet images of the corona, not because they are cold in any ordinary sense, but because the plasma within them is thinner than the surrounding closed-loop regions. Less material, less emission, darker appearance. They are called coronal holes, and they are the source of the solar wind's fastest and most energetic component. During the quietest phases of the 11-year solar cycle, large and persistent coronal holes occupy both polar regions of the Sun. They are not small features. A polar coronal hole at solar minimum can extend from the pole itself down to latitudes of roughly 60 degrees, or even further, covering an enormous fraction of the Sun's upper or lower hemisphere. Their boundaries are not clean straight lines. They wander irregularly across the high latitudes, with irregular bays and peninsulas of open magnetic territory pushing into the surrounding closed corona. The shapes shift over weeks and months, but the overall presence of a large, stable polar coronal hole during the quiet phase of the cycle is one of the most persistent and reliable features of the Sun's behavior. From these polar holes, the solar wind streams outward at roughly 700 to 800 kilometers per second. Pause on that number for a moment. 700 to 800 kilometers per second. In a single second, A parcel of plasma born in a polar coronal hole travels a distance greater than the diameter of the Earth. In the time it takes you to draw a single breath, that plasma has crossed a distance comparable to the gap between Earth and the Moon. This is the fast solar wind, and it is nearly twice the speed of the slow solar wind that originates from the equatorial regions of the Sun. The slow wind drifts outward at roughly 300 to 500 kilometers per second, still an extraordinary velocity by any ordinary standard, but measurably, consistently slower than the polar fast wind. It originates not from large open coronal holes, but from the boundaries between open and closed field regions at lower latitudes, and from a broad equatorial band called the streamer belt, where the Sun's magnetic field forms the bright looping structures most visible during total eclipses. The two winds are not merely different in speed, they differ in composition, in temperature profile, in density variability, in the ratio of certain heavy elements relative to hydrogen. The fast wind is smoother, more uniform, less turbulent. The slow wind is more variable, more turbulent, more complex in its fine-scale structure. These differences reflect the different environments from which each wind originates: the clean, open field of the polar holes on one hand, and the tangled, partially closed field of the equatorial streamer belt on the other. The two winds exist simultaneously throughout the inner solar system, streaming past the planets in alternating patterns as the Sun rotates and presents different regions to face the planets in turn. Where fast wind overtakes slow wind that departed earlier from a different solar longitude, the two streams collide. Compression fronts form, magnetic boundaries develop. The interaction regions between fast and slow solar wind are among the most turbulent and energetically rich structures in the inner heliosphere, and they are a direct consequence of the difference between what the poles produce, what the equator produces. Where the two wind regimes meet, and threading through the entire structure of the heliosphere at large, lies one of the most remarkable magnetic structures in the solar system. The Sun's magnetic field has, at the largest scale, a direction. One hemisphere, the one containing the north magnetic pole, carries field lines pointing outward from the Sun. The other carries field lines pointing inward. These two hemispheres of opposite magnetic polarity are separated by a surface, a thin, mathematically defined boundary, where the field direction flips from outward to inward. This surface does not sit flat along the solar equator. It undulates. It warps above and below the equatorial plane with a rhythm set by the Sun's own rotation and by the large-scale structure of the coronal magnetic field. As the Sun rotates, this undulating magnetic boundary sweeps through space in a slowly expanding spiral pattern, carried outward by the solar wind. The result is a vast, rippling surface, extending from the inner solar system outward past all the planets, a slowly turning, slowly warping membrane of magnetic structure filling the entire heliosphere. It is called the heliospheric current sheet, and it is the largest coherent magnetic structure in the solar system. It has been described, often, as resembling the skirt of a spinning dancer. As the Sun turns, the hem of the skirt rises and falls rhythmically, sweeping past each planet in a slow, regular cadence. Earth crosses the heliospheric current sheet multiple times during each solar rotation. Each crossing brings a reversal of the local magnetic field direction, a small but measurable change in the magnetic environment immediately around the planet. During periods of elevated solar activity, these crossings can contribute to minor disturbances in Earth's own magnetic field. The shape of the current sheet changes with the solar cycle. Near solar maximum, when the Sun's magnetic field is most disordered and the corona most complex, the sheet is wildly tilted, its crests and troughs reaching steeply away from the equatorial plane, sometimes extending to latitudes that would have been unthinkable during quieter periods. Near solar minimum, the sheet flattens toward the equatorial plane, its ripples gentle and regular, its geometry as calm as the Sun's behavior becomes during those quiet years. No direct image of the full heliospheric current sheet has ever been made. Its shape is inferred, reconstructed from in situ measurements taken by spacecraft that pass through it, and from coronal images taken from inside the plane. A sustained view from above the disk would, for the first time, allow the sheet's true three-dimensional geometry to be observed rather than inferred. The slowly spinning, slowly warping membrane of magnetic structure seen in plan view, from a perspective that could take in the whole pattern at once, spreading outward past the orbits of the planets. That image does not yet exist. Roughly every 11 years, the Sun's global magnetic field reverses polarity. What was the north magnetic pole becomes the south. What was the south becomes the north. This reversal is not a sudden event. It does not happen in an instant or even in a single season. It is a gradual process that unfolds across years, driven by the slow migration of magnetic flux from the active regions at lower latitudes toward the poles, and it is one of the most consequential recurring events in the entire solar system. The reversal originates at the poles. Throughout each solar cycle, active regions, sunspot groups, and their associated magnetic structures emerge predominantly at mid-latitudes and carry magnetic flux of specific orientations. One polarity in each pair of sunspots consistently leads the other as the Sun rotates. The trailing polarity, through a combination of diffusion and slow, large-scale flows in the solar atmosphere, migrates poleward over the months and years following each emergence. This poleward drift carries flux of the opposite polarity from what currently exists at each pole. As the accumulated opposite polarity flux reaches the poles and builds up in sufficient quantity, it cancels the existing polar field and eventually overwrites it, flipping the polarity and completing one half of the full 22-year magnetic cycle. The two poles do not always reverse at exactly the same moment. One hemisphere often leads the other by months, occasionally by more than a year. During these intervals, the Sun briefly carries a magnetic structure more complex than a simple dipole, a configuration with multiple poles at unusual latitudes, a temporarily quadrupolar geometry that produces distinctive signatures in the corona and in the solar wind. The asymmetry resolves itself as the lagging pole eventually catches up, and the Sun settles back into a clean dipole oriented in the new direction. The strength of the polar magnetic field at the end of one cycle, the residual field that remains after the reversal has completed and the new polarity has established itself, appears to be one of the better predictors of how strong the next solar cycle will be. A robust polar field at cycle minimum tends to precede a vigorous sunspot cycle 11 years later. A weak polar field tends to precede a weaker cycle. The connection is not absolute, and the precise mechanisms linking polar field strength to future cycle amplitude are still being worked out. But the correlation is strong enough that solar physicists monitor polar field measurements as one of their most reliable inputs for forecasting upcoming solar activity. This makes the poles, in a very real sense, the engine room of the Sun's long-term behavior. The activity that dominates the equatorial view, the sunspots, the flares, the eruptions, the radio bursts, the geomagnetic storms at Earth, is the visible output of a process whose cause and memory both reside at latitudes almost never observed directly. The visible surface of the Sun near the poles, in the limited views available from within the ecliptic, appears structurally different from the equatorial surface. The broad, active regions and large sunspot groups that dominate equatorial latitudes are absent from the high-latitude polar zones. Instead, the magnetic field near the poles breaks into countless small concentrations, a fine, tangled network of tiny magnetic bundles woven through the granular surface texture of the solar photosphere, the visible outer layer of the Sun. The granulation pattern itself, the familiar cellular texture of the solar surface, bright cells where hot plasma rises and dark lanes where cooler plasma descends, each cell a few hundred kilometers across, covers the polar regions as it covers everything else. But threaded through this granulation near the poles, the magnetic field emerges in small bundles rather than in the concentrated, organized structures of mid-latitude active regions. The polar surface, at the resolution available from inside the plane, looks quieter than the equatorial surface, more diffuse, more granular, less visibly dramatic. Above this surface, thin streams of plasma, called polar plumes, extend outward along the open magnetic field lines, like slender columns of slightly denser material threading through the surrounding fast wind. The plumes are best observed during total solar eclipses, when the moon's disk briefly blocks the blinding photosphere and the faint corona becomes visible to careful eyes and sensitive instruments. Seen from within the plane, the plumes appear as delicate rays curving away from the sun's polar limbs, faint, quiet, easily overlooked against the brighter structures of the equatorial corona. Seen from directly above a pole, they would appear as a radiating pattern, individual columns spreading outward from the pole in every direction, like the petals of a very slowly turning flower. Each plume, a thin thread of denser plasma among the surrounding fast wind, aligned with the open field lines reaching away from the polar coronal hole into the wider heliosphere. You might try for a moment to hold that image. The sun seen not as a disk, but as a sphere, viewed from directly above one of its rotation poles. The familiar sunspot activity of the equatorial regions invisible, hidden below the horizon of the curved surface. The polar surface below you, textured with granulation, threaded with small magnetic bundles, the polar plumes radiating outward in a slow geometric flower, the fast wind streaming away in long, straight rays. The polar coronal hole vast, dark in ultraviolet light, stable, open, covering much of the hemisphere below your vantage. The geometry would feel less like the star familiar from equatorial photographs and more like looking down into the open eye of something immeasurably patient and very old. The polar regions also govern the sun's behavior on timescales far longer than the 11-year cycle. There are periods in the historical record visible in the proxy records of carbon isotopes preserved in tree rings and ice cores, and in the fragmentary written records of sunspot sightings going back several centuries when the sun's activity dropped noticeably for decades at a time. Sunspot cycles became weak and infrequent. The corona during eclipses appeared simpler and less structured. The polar regions during these extended quiet intervals are thought to have sustained weaker than average magnetic fields across multiple consecutive cycles, producing the suppressed activity that the proxy records preserve. The connection between polar field strength, sustained over many cycles, and the sun's behavior on decadal and centennial timescales is one of the more consequential open questions in solar physics. It touches on questions about the sun's influence on Earth's climate across long periods, about the variability of the radiation environment throughout the inner solar system, about the long-term behavior of the heliosphere itself. All of these questions lead back, eventually, to the poles. The pattern of solar activity across a cycle also traces the poles' influence in a different way. Sunspots emerge preferentially at mid-latitudes early in each cycle, and their average emergence latitude drifts systematically toward the equator as the cycle matures. Charted over many cycles, this pattern produces the famous butterfly diagram of solar activity, a repeating shape that looks, when drawn on a graph of latitude versus time, like the paired wings of a butterfly, with each cycle's activity beginning at high latitudes and migrating equatorward across the 11 years. The wings of each butterfly begin at roughly the same latitude, where the poleward drifting magnetic flux of the previous cycle originated. The poles set the starting latitude of the next cycle's wings. They are, in this sense, the point of origin from which the visible activity of each cycle propagates. The differential rotation of the solar surface adds another layer. The sun does not rotate as a rigid body. Its equator completes one rotation in approximately 25 days. Its polar regions take more than 30 days to complete the same rotation. This gradient of rotation rates faster at the equator, slower at the poles, stretches, and winds the sun's magnetic field over the course of each cycle, building up the complex twisted structures that eventually produce sunspots and active regions. The poles, rotating most slowly, set one end of the differential rotation gradient that drives the entire magnetic cycle. They are simultaneously the slowest rotating part of the visible surface, and the site where the cycle's accumulated magnetic flux is finally stored, reversed, and carried into the next cycle. Beneath the visible surface, the deep interior of the sun also rotates differentially, with patterns that can be probed by listening to the sun's own acoustic oscillations, pressure waves that travel through the interior and modulate the brightness of the visible surface in detectable ways. The technique is called helioseismology, and it has revealed that the interior rotation pattern is complex, varying with both latitude and depth. The boundary layer between the deep, radiative interior, which rotates nearly uniformly, and the outer convective layer, which rotates differentially, is thought to be one of the primary sites of magnetic field amplification in the Sun. The poles play a role in this deep interior architecture as well, though the details of how the polar surface field connects to the deep interior processes remain an active area of research. The overall picture that emerges from decades of solar observation, from ground-based observatories, from spacecraft within the ecliptic, from the limited high-latitude data gathered by the two missions that will occupy the next part of tonight, is that the Sun's magnetic cycle is a long chain of interconnected processes. It begins in the deep interior, where magnetic field is amplified by differential rotation. It propagates upward through the convective layer, emerging at the surface as sunspots and active regions. It migrates poleward across the years of each cycle through the slow drift of magnetic flux. It accumulates at the poles, cancels the existing polar field, and reverses the polarity, storing in the new polar field the conditions that will seed the amplitude and character of the next cycle 11 years hence. The poles are simultaneously the end point of each cycle and the starting point of the next. They hold the Sun's magnetic memory from one phase of its behavior to another, across timescales of decades and apparently of centuries, and they are the regions about which least is known. Not because they are unimportant, not because solar physicists have overlooked them, but because the geometry of where we are placed in the solar system inside the disk, within the plane, at the equatorial vantage that every spacecraft inherits from the planet it departed, makes the poles genuinely difficult to observe with the clarity their importance demands. The Sun has been cycling, reversing, streaming its polar wind, storing its magnetic memory for 4.5 billion years. For essentially the entire history of solar physics as a discipline, the polar regions have been observed at best in foreshortened glimpses, partially resolved, geometrically compromised, the detail lost in the shallow angle of view available from within the ecliptic. What has been learned from those glimpses is already enough to establish that the poles matter deeply. What remains unknown, what a sustained, properly positioned polar vantage would reveal, is the subject of serious ongoing scientific discussion. Two missions have attempted, in their different ways, to provide something closer to that vantage. Neither has fully succeeded. Both have changed what is known. Together, they represent the entirety of human experience above the plane of the planets. Their stories come next. Only two spacecraft in the entire history of human spaceflight have ever climbed meaningfully out of the ecliptic to observe the Sun's polar regions from an elevated vantage. Both stories are remarkable. Both are incomplete. One reached high solar latitudes but carried no instrument capable of photographing the Sun's surface directly. The other is currently in operation, climbing gradually out of the plane through a patient sequence of planetary flybys, and has only very recently returned the first close direct images of a solar pole ever obtained by any spacecraft. Together, they represent the whole of human experience above the plane of the planets. Neither has been able to hover. Neither has held a fixed position above a pole while the Sun rotated beneath it. Both have been moving continuously on their own inclined orbits, sampling the polar regions during the brief intervals when their trajectories carried them high enough above the disk, then sweeping back toward lower latitudes as the orbits continued their loops. The observation has always been a passing glance rather than a sustained gaze. But the glances have changed everything that was previously known. The first mission to climb above the ecliptic was a collaboration between two space agencies, one from North America and one from Europe, planned across many years of scientific negotiation and engineering development, and launched from low Earth orbit aboard a winged orbital vehicle in the early 1990s. The spacecraft itself was small by interplanetary standards, a single large dish antenna for communicating with Earth, a spinning body designed to keep its complement of instruments distributed evenly around its axis, sampling the space environment in all directions simultaneously rather than pointing at a fixed target. It carried instruments for measuring magnetic fields, for counting and characterizing solar wind particles across a range of energies, for detecting energetic ions accelerated by solar flares and interplanetary shock fronts, for registering the impacts of individual dust grains, for monitoring radio and plasma wave emissions, and for measuring the populations of galactic cosmic rays arriving from outside the heliosphere. What it did not carry was a camera. There was no high-resolution telescope aboard capable of imaging the Sun's surface or its detailed coronal structure. The mission's scientific purpose was to characterize the physical environment at high solar latitudes to measure what was then not to photograph what it looked like. The visual appearance of the polar sun, the actual texture of the polar surface, and the structure of the polar corona seen from above remained beyond what this first mission could address. The trajectory this spacecraft flew was one of the most elegant pieces of mission design ever executed in the history of planetary exploration. The spacecraft did not launch toward the sun, it launched away from it outward, on a long curving path toward Jupiter, the largest planet, the most powerful gravitational slingshot available anywhere in the solar system. The journey to Jupiter took approximately 16 months. At Jupiter, the spacecraft executed a precisely timed flyby at a carefully calculated approach geometry, skimming close enough to the giant planet to extract an enormous gravitational assist, one that no chemical rocket could have provided from Earth. The flyby redirected the spacecraft's trajectory sharply out of the plane of the planets. After the encounter, the orbit was tilted by approximately 80 degrees relative to the ecliptic, nearly perpendicular to the plane of everything else in the solar system. The spacecraft then began looping around the Sun on this steeply inclined orbit, climbing high above the ecliptic at one extreme of each loop, diving deep below it at the other, passing through the plane between. Each loop carried it over one solar pole or the other, sampling the environment at progressively higher latitudes as the orbit geometry evolved. The maneuver was extraordinary, precisely because it could not have been accomplished any other way. The delta V required to tilt an orbit by 80 degrees through direct thrust from low Earth orbit would have exceeded 30 kilometers per second, more than any chemical rocket combination ever assembled could have delivered, to a spacecraft of any useful size. By taking the detour to Jupiter first, and using Jupiter's gravity to provide essentially all of the inclination change, the mission accomplished what no direct ascent could have done at all. It was the first practical demonstration that the solar polar regions, while genuinely expensive to reach in energy terms, were not permanently beyond reach, provided the mission was patient enough and clever enough with the gravitational resources available along the way. The trajectory took years longer than a hypothetical direct climb would have required, but the direct climb was never actually available. Only the Jupiter detour was available, and the Jupiter detour worked. The scientific return from this first polar mission was substantial, and in certain respects, it was transformative. The mission confirmed for the first time, through direct in situ measurement, what had previously been inferred from ground-based observations and theoretical modeling, that the fast solar wind originates predominantly from the polar regions of the Sun, and that the slow wind comes from the equatorial streamer belt. Before this spacecraft flew, the association between high-latitude coronal holes and the fast wind was a reasonable theoretical expectation supported by indirect evidence. After this mission flew through both polar regions and measured the wind speed, density, temperature, and composition at each latitude, the picture was confirmed by direct observation for the first time. The fast wind was there, streaming outward from the polar coronal holes at the speeds the models had predicted, carrying the compositional signatures that distinguished it from the equatorial slow wind, uniform and smooth in a way that the turbulent slow wind was not. The polar origin of the fast wind passed from inference to established fact. The mission also confirmed the broad geometry of the heliospheric current sheet, the vast undulating magnetic boundary that separates the two hemispheres of the Sun's large-scale field. As the spacecraft climbed to higher solar latitudes, its crossings of the current sheet became less frequent, exactly as expected if the sheet were a roughly equatorial structure, warping only modestly into higher latitudes during quiet solar conditions. The geometry of the current sheet as a function of latitude and solar cycle phase was mapped from a perspective that could actually track how the structure changed with elevation above the plane, something that no in-plane spacecraft could have accomplished. A less anticipated discovery concerned the large-scale structure of the Sun's magnetic field at distances well beyond the immediate polar regions. The field was strongly polar in character near the surface, and in the immediate vicinity of the polar coronal holes, clean open field lines extending outward from the holes in the pattern the models had predicted. But at greater distances from the Sun, the radial component of the heliospheric magnetic field was found to be surprisingly uniform with solar latitude. Once the spacecraft was well clear of the polar region itself, the outward pointing component of the field became roughly the same in all directions, smoothed by the way that the solar wind plasma carrying the field outward redistributes the magnetic flux across the heliosphere. The structure of the field was, in other words, more local than expected near the Sun and more globally uniform than expected at distance. The transition between these two behaviors, between the organized polar geometry near the source and the latitude-independent uniformity far away, was something no prior observation had been positioned to detect. The mission also sampled environments no spacecraft had previously entered. High above the disk, well outside the plane of the planets, the populations of galactic cosmic rays were measured for the first time at high heliospheric latitudes. The question of how cosmic rays' energetic particles arriving from sources distributed throughout the galaxy penetrate the heliosphere from above and below, rather than through the equatorial plane where most prior measurements had been made, could finally be addressed with direct data. The flux of cosmic rays at high latitudes told astronomers something about how the heliosphere's magnetic structure modulates the incoming galactic background in the polar directions, information that the geometry of in-plane observation had previously made inaccessible. The interstellar dust instrument detected grains drifting into the solar system from outside particles whose motion and physical characteristics distinguished them from the locally produced dust of the planetary plane, identifiable as genuine interstellar material arriving from the direction of the Sun's motion through the galaxy. The polar vantage made it possible to characterize this interstellar dust component with less contamination from the concentrated local dust of the ecliptic plane. The mission operated for nearly 2 decades before its power systems declined below the threshold needed to maintain all instruments, and the mission was formally concluded. The orbit it traced, the high-inclination loop around the Sun that Jupiter's gravity had carved for it, continues to exist. The spacecraft follows it still, inert now, its antenna silent, its instruments long since powered down. The orbit itself is one of the more poignant artifacts of the space age. A perpetual high-inclination trajectory around the Sun, carrying its silent passenger above and below the disk on a schedule no one is monitoring anymore, on a path that will persist for as long as the gravitational geometry that sustains it remains undisturbed. There is no rescue planned. There is no successor flying the same orbit. What the first mission could not do, for all its scientific accomplishments, was look. It could measure the wind. It could not photograph the surface it came from. It could measure the magnetic field at high latitudes. It could not image the magnetic structures whose field it was measuring. The visual landscape of the polar Sun, the actual appearance of the surface and corona seen from above, remained almost entirely unknown when the mission ended. The closest thing to a polar image that existed before recently was a foreshortened view from within the ecliptic, the pole tilted toward the observer at a shallow angle, most of the detail compressed and lost in the geometry of projection across the curved stellar limb. The poles had been visited in the only sense available to a mission without cameras. They had not yet been seen. Decades after the first mission concluded, a second spacecraft was launched with a fundamentally different strategy for reaching high solar latitudes and with a full suite of imaging instruments specifically designed to address what the first mission had been unable to provide. Rather than using a single large gravity assist from Jupiter to tilt the orbit sharply all at once, this second mission uses repeated close flybys of Venus to accumulate inclination gradually, one small orbital tilt at a time. Each Venus encounter adds only a few degrees to the orbital inclination. The process is patient. Many flybys are required across many years of mission operations, but patience costs nothing in propellant, and the spacecraft climbs steadily out of the plane with each successive encounter, reaching progressively higher solar latitudes with each loop around the Sun as the accumulated inclination grows. The instrument suite aboard this second mission was designed as a deliberate complement to what the first mission lacked. There is a high-resolution telescope for imaging the solar surface at visible wavelengths. There is a magnetograph capable of mapping the surface magnetic field directly, producing images in which the strength and direction of the field at each point on the visible surface can be read at a glance. There are ultraviolet images for capturing the structure of the chromosphere and corona at the wavelengths where hot plasma emits most of its radiation. There are coronagraphs that use small occulting disks to block the blinding photosphere and reveal the faint outer corona in white light. And there are the same complement of in situ particle and field instruments that the first mission carried, measuring the local plasma environment around the spacecraft as it moves through different heliospheric latitudes. The result is a flying solar observatory designed to give the polar regions the same multi-layered observational treatment that equatorial regions have received from ground-based and space-based instruments for generations. The orbit of this second mission takes it unusually close to the Sun at perihelion, the nearest point of each elliptical loop. Close enough that thermal engineering is among the most demanding aspects of the mission design. A specialized heat shield faces the Sun at all times during the close approaches, protecting the spacecraft body and instruments from the intensity of sunlight at those distances. The shield's outer surface is treated with a specialized coating to reflect away as much solar radiation as possible. Small apertures in the shield allow the optical instruments to look outward briefly during the portions of each orbit, when the spacecraft is distant enough from the Sun for the thermal environment to be manageable. The close perihelion passes are not merely a thermal challenge, they are also scientifically valuable in their own right, providing measurements of the solar wind and magnetic field at distances from the Sun that no previous mission had sampled, in the region where the wind is still being accelerated and structured before it reaches the distances where all prior observations had been made. As the mission has progressed, and the cumulative effect of successive Venus flybys has tilted the orbit further from the ecliptic, the spacecraft has begun reaching latitudes from which the polar regions of the Sun become visible at meaningful angles. The foreshortening that limits equatorial observations of the poles does not disappear immediately. Even at 20 or 30 degrees of orbital inclination, the polar surface is still seen at a significant angle. But the view improves with each successive inclination increment, and as the mission continues its patient climb, the polar perspective sharpens. The first direct close images of a solar pole returned by this mission, when they arrived, did not resemble the equatorial surface that decades of solar observation had made familiar. The surface texture was finer and more complex. The broad, organized active regions and large sunspot groups that dominate equatorial latitudes were absent. In their place, a dense tangle of small magnetic features, countless individual flux concentrations scattered across the granular surface rather than gathered into the structured groups of lower latitudes. The polar magnetic field appeared at the surface not as a few large organized structures but as a fine, intricate network of small elements, woven through the granulation in a pattern unlike anything in the well-studied equatorial archive. The polar plumes, those thin columns of slightly denser plasma extending outward from the polar coronal hole along open magnetic field lines, were resolved as individual structures for the first time, from a perspective that allowed their three-dimensional geometry to begin to be assessed. Not the compressed, foreshortened rays visible from the ecliptic during eclipses, but actual columns seen at an angle that revealed something of their true extent and spacing. It was the first time human instruments had ever seen the Sun from this direction at any meaningful resolution. There is no archive of polar solar images predating these frames. There is no collection of historical polar observations against which these new views can be compared. The polar surface of the Sun is, in the most literal observational sense, new territory. The frames returned by this mission represent the beginning of a polar image archive. The the first entries in a catalogue that did not previously exist. What the two missions together have established is what could not have been known from within the plane alone. The first mission proved by direct measurement that the polar environment is physically different from the equatorial one. Different wind speed, different composition, different magnetic structure, different cosmic ray access. The confirmation transformed theoretical inference into observed fact and defined the physical character of the high-latitude heliosphere for the first time. The current mission is filling in what the first mission could not provide: direct imagery, magnetic mapping, ultraviolet structural mapping of the polar corona, the actual visual appearance of the polar surface and its overlying atmosphere. The Polar Science Archive that is beginning to accumulate represents something qualitatively new, observational data of a kind that simply did not exist before. Between them, the two missions have demonstrated that a vantage point above the ecliptic is not a convenience for solar physics. It is a requirement. The Sun is a three-dimensional object. Its poles are not peripheral regions. They are central to the processes that govern its behavior across timescales from days to centuries. Understanding the Sun fully means observing it fully from every relevant angle, including the angles that the geometry of the solar system makes hardest to reach. Even so, what both missions combined have observed is a small fraction of what a sustained polar observatory could provide. Neither spacecraft has been able to hover above a pole. Neither has held a fixed polar position while the Sun turned through its daily and seasonal rhythms beneath. Both have been moving past on their inclined orbits, gathering polar data during the intervals when their trajectories carried them high enough, then descending toward lower latitudes as each loop continued. The polar observation has always been a passage rather than a residence. A mission capable of sitting above a solar pole for years at a time, observing the polar surface continuously through a full solar rotation, tracking the evolution of polar coronal holes through the rise and fall of an entire solar cycle, watching the approach of the magnetic polarity reversal from the vantage that would make its mechanism most visible has not yet been built. The polar story of the Sun that would require that kind of sustained observation is still incomplete. The progress already achieved is enormous relative to the long baseline of having no polar observations at all. The remaining gap is also enormous relative to what a true polar station could provide. Both things are simultaneously true. The two missions are an opening into a vantage that was closed for the entire history of solar physics. They are also a first step into a territory that remains, by any reasonable measure, almost entirely unexplored. The polar sun has been glimpsed. It has not yet been known. The instruments, the data systems, the communication architectures, the thermal designs, the trajectory calculations, all of this engineering understanding exists and has been demonstrated. What has not yet been assembled is the mission that would use all of it to finally take up residence above the disk and remain there long enough to watch the sun as it has never been watched before. The engineering for that mission already exists. The mission does not. The sun's influence does not end at the orbit of the outermost planet. The solar wind, that continuous outward stream of charged plasma born in the corona and accelerating through the inner solar system, does not simply stop when it passes Neptune or crosses the boundary of the planetary disk. It continues outward, thinning gradually as it spreads across an ever larger volume of space, carrying the sun's magnetic field with it, pushing against the surrounding interstellar medium in every direction simultaneously. Eventually, at some distance far beyond the planets, the outward pressure of the wind and the inward pressure of the surrounding interstellar gas reach equilibrium. A boundary forms. The outward flow slows, piles up, and is deflected, and everything enclosed within that boundary, every planet, every moon, every asteroid, every comet, the entire disk of the solar system, the vast outer reservoir of icy bodies that surrounds it, all of it, sits deep inside a single enormous bubble of solar plasma. That bubble is called the heliosphere, the boundary where the solar wind finally surrenders to the surrounding interstellar pressure is called the heliopause. Beyond it lies the local interstellar medium, the thin gas and dust and magnetic field of the space between stars, unchanged by the sun's output, belonging to the galaxy at large rather than to our local star. The heliosphere is our home in a more fundamental sense than the solar system alone. It is the region of space shaped by the sun's activity, protected from the harsher particle environment of interstellar space by the sun's own outward wind. The galactic cosmic rays that fill the Milky Way high-energy particles accelerated by distant supernova remnants and other energetic processes throughout the galaxy are partially deflected and moderated by the heliosphere's magnetic structure before they reach the inner solar system. Without the heliosphere, the cosmic ray environment at Earth's surface would be meaningfully more intense. The bubble is not merely a geometric curiosity, it is a shield, and its shape is one of the significant open questions of contemporary astronomy. For most of the late 20th century and into the early years of the 21st, the standard mental picture of the heliosphere was simple and intuitive. The sun moves through the surrounding interstellar medium at roughly 26 kilometers per second relative to the local gas. This motion, the thinking went, should compress the heliosphere on the side facing the direction of travel, the upwind side, where the moving sun pushes into the gas it encounters, and stretch it out into a long, extended tail on the downwind side, where the solar wind flows away in the direction the sun has come from. The resulting shape, in this picture, resembles a comet, a rounded, blunt nose on the upwind side where the boundary is closest to the sun, a long, gradually narrowing tail extending many times further on the downwind side, potentially reaching hundreds of astronomical units beyond the planetary system before the wind finally mixes completely with the surrounding interstellar gas. The comet-shaped picture was not arbitrary. It was grounded in the same physics that produces genuine cometary tails, the interaction between an outward-flowing particle stream and a surrounding medium, producing compression on one side and extension on the other. Observations of similar bubble-like structures around other moving stars elsewhere in the galaxy supported a broadly cometary geometry. The model fit a large portion of the available data. For decades, it was the working picture, reproduced in textbooks and review articles and public explanations of what our solar system looks like from outside. Then the measurements became more precise, and the picture began to complicate. Two spacecraft launched in the early 1970s have, across the decades since, traveled further from the sun than any other human-made objects in history. Both were sent initially to survey the outer planets, one visiting Jupiter and Saturn before continuing outward, the other visiting all four giant planets in a rare alignment that made such a grand tour possible. After completing their planetary surveys, both continued on trajectories carrying them out of the solar system entirely, away from the sun at speeds that no subsequent mission has matched. Both have now crossed the heliopause and entered interstellar space. The first crossing came in the early 2010s, the second followed several years later. The crossings were identified by specific signatures in the data, abrupt changes in the density and character of the plasma surrounding each spacecraft, and changes in the magnetic field direction consistent with transitioning from the heliospheric environment to the local interstellar medium. These crossings represent the only direct in-situ measurements ever made of the heliopause itself. They are the only moments in human history when an instrument built on Earth has sampled the actual boundary of our local bubble. Both crossings occurred in roughly the same general region of the heliosphere near the upwind nose, the side facing the direction of the sun's motion through the interstellar medium, and broadly within the plane of the planets. Neither spacecraft was able to probe the tail, neither was positioned to measure the boundary from above or below. The sample of the heliopause that humanity possesses consists of two data points, both in roughly the same direction, both from within the disk. And what those two data points revealed was richer and stranger than the simple comet model had anticipated. A different picture of the heliosphere's shape has emerged from a combination of the boundary crossing data, measurements of energetic neutral atoms streaming inward from the boundary region, and theoretical work on how the interstellar magnetic field, which the comet model had largely ignored, interacts with the sun's own field at the heliopause. In this alternative picture, the heliosphere does not have a long, extended tail. Instead, it has two lobes, two roughly symmetric extensions, curving back from the upwind nose separated by a narrow waist, with the overall shape resembling not a comet, but something more like a deflated sphere pinched at the sides, or a shape reminiscent of a crescent seen in cross-section. The mechanism that produces this different geometry is the interstellar magnetic field threading through the gas surrounding the heliosphere. That field exerts a pressure on the heliopause. The direction of the interstellar magnetic field is not aligned with the direction of the Sun's motion, and the oblique angle between them distorts the boundary in ways that prevent the simple cometary extension from developing. The Sun's own magnetic field, carried outward by the solar wind and concentrated near the heliopause, also resists the formation of a long tail. The magnetic pressure in the downwind region pinches the boundary closed rather than allowing it to stretch indefinitely. In this model, the heliosphere is more compact than the comet picture suggested. The boundary on the downwind side sits not many hundreds of astronomical units away, but at a distance comparable to the upwind boundary, the bubble roughly symmetric rather than dramatically elongated. The two models make different predictions for the distribution of energetic neutral atoms arriving from the boundary region. These atoms are produced when outward-flowing solar wind ions interact with inward-drifting neutral atoms from the interstellar medium charge exchange, reactions that create fast neutral particles no longer bound by the heliospheric magnetic field, free to travel inward in straight lines toward the inner solar system where instruments can detect them. The directions and energies of these arriving neutral atoms carry information about where the interactions occurred, and therefore about the geometry of the boundary region. An earlier in-plane mission designed specifically to map these incoming neutral atoms across the full sky produced the first all-sky maps of the heliospheric boundary inferred from this technique. The maps revealed an unexpected feature, a bright ribbon of enhanced emission stretching across the sky in a particular geometric pattern apparently associated with the direction of the local interstellar magnetic field. The ribbon's existence was not predicted by the simpler models. Its presence demonstrated that the boundary region has more structure than the most straightforward pictures had assumed. A more capable mission designed to map the same neutral atom flux with significantly higher resolution and sensitivity is being prepared. It will orbit relatively close to Earth and build up much sharper maps of the heliospheric boundary from the inside, allowing the comet-shaped and croissant-shaped models to be tested against observations with a precision not previously available. The mission will refine our understanding of the bubble's shape without requiring a spacecraft to actually travel to the boundary, inferring the three-dimensional geometry from the patterns of inward-traveling particles, the way a medical imaging instrument reconstructs internal structure from signals arriving from many angles simultaneously. The technique is powerful, but it is indirect. It maps by inference rather than by direct observation. A spacecraft positioned above the ecliptic, climbing out of the disk on a high-inclination orbit, could approach the boundary from a direction that no existing or planned mission will sample. Direct measurements of the magnetic field and plasma at high heliospheric latitudes would discriminate between the two competing models in ways that in-plane measurements cannot. The comet model and the croissant model predict different field geometries at high latitudes. They predict different plasma distributions. They predict different distances to the boundary in the polar directions. A spacecraft traversing the high-latitude heliosphere on an outward-bound trajectory would pass through regions where the two models disagree, returning measurements that would resolve the ambiguity. If the spacecraft eventually crossed the heliopause from above or below, entering interstellar space in the polar direction, rather than through the equatorial nose, it would return the first boundary measurements ever made outside the disk. The third data point in humanity's direct sample of the heliopause, taken from a direction that no prior mission has approached. Either outcome would be transformative. Confirming the cometary tail would clarify how the interstellar magnetic field permits the Sun's wind to extend so far downwind before losing coherence. Confirming the croissant geometry would revise the fundamental picture of our local bubble and imply that the boundary is closer to the Sun in the polar directions than the textbook model had suggested. And whatever the shape turns out to be, the first measurement of the heliopause in the polar direction would extend the map of our home into a region that currently has no data at all. The portrait of the heliosphere remains incomplete, not because the boundary is unreachably distant. The upwind heliopause sits at roughly 120 to 150 astronomical units from the Sun. The polar boundary, in either model, is not dramatically further. It is incomplete because every instrument ever sent toward the boundary has been sent from within the disk, along trajectories that the disk's geometry permitted. The polar directions have never been approached. The boundary in those directions has never been sampled. We have measured 2 points on the surface of our bubble, both in the same general direction. The rest of the surface, most of it, including the entire polar extent, remains unvisited. The heliosphere is not a static object frozen in a single configuration. It breathes. As the solar cycle rises toward maximum, the solar wind intensifies more material leaving the Sun, carrying more energy, pushing the boundary further outward. The heliopause moves away from the Sun during active solar periods. As the cycle descends toward minimum and the wind quiets, the boundary retreats inward. The 2 spacecraft that crossed the heliopause did so at different phases of the solar cycle, and their measured crossing distances reflected the cycle's state at those particular moments. The boundary they each crossed was not the same boundary, it was the same structure at 2 different points in its slow expansion and contraction. The interstellar medium on the other side of the boundary also varies. The Sun is currently drifting through the local interstellar cloud, a relatively thin region of interstellar gas embedded within the larger and even thinner local bubble carved by ancient supernova explosions. The boundaries and internal structure of the local interstellar cloud are not perfectly uniform. Different directions from the Sun sample slightly different densities and magnetic field orientations in the surrounding gas. These variations affect the shape and distance of the heliopause in different directions in ways that no single set of measurements, however detailed, could fully characterize. When the Sun eventually drifts beyond the local interstellar cloud into whatever denser or thinner region lies beyond it, the heliosphere will change. A denser external environment would compress the bubble. A thinner one would allow it to expand. The heliosphere has not always been the size and shape it is today. Over the 4.5 billion years of the solar system's history, as the Sun has traversed different environments in its long orbit around the galactic center, the bubble it carries with it has expanded and contracted, changed shape, adapted to the changing external pressure. The heliosphere we inhabit now is the current one appropriate to the current external conditions, and temporary in the way everything in an evolving universe is temporary. Beyond the heliopause, the local interstellar medium extends outward to the boundaries of the local bubble, the larger cavity, carved by the supernovae of massive stars that lived and died in this region of the galaxy tens of millions of years ago. The walls of that larger cavity glow in soft X-rays. The interior of the cavity, through which the Sun is currently drifting, is among the lower density regions of interstellar space in this part of the galaxy. The direction below the Sun's south pole, in galactic terms, opens into one of the clearer sightlines through this cavity toward the wider galaxy, beyond a direction of relatively low foreground obscuration that would provide a particularly clean observational window for a telescope positioned at high solar latitudes. You can hold for a moment the full nested picture of where you are. A planet orbiting a star, the star surrounded by a bubble of its own wind, the bubble drifting through a thin region of interstellar gas. That thin region embedded within a larger cavity, hollowed out by ancient stellar explosions. That cavity sitting within a spiral arm of a galaxy containing several 100 billion stars. That galaxy the largest member of a small local cluster of galaxies. That cluster itself a minor feature of the vast cosmic web of filaments and voids that constitutes the large-scale structure of the observable universe. Each layer wraps the next. Each has its own shape, its own physics, its own history. Each was produced by the same underlying laws, operating at different scales and over different timescales. Gravity, rotation, pressure, the slow, patient logic of physics working through whatever material is available. The question that has been threading through tonight, the question of what sits above and below the Sun, what the plane of the solar system looks like from outside its own flatness, What the shape of our local bubble actually is in part a question about how clearly we can see all of those nested layers from where we happen to be placed. From inside the disk, we see them through the geometry that contains us. From above the disk, we would see them through far less. The portrait of our home is incomplete, not because the universe is inaccessible, not because the relevant distances are prohibitive, not because the physics is unknown or the engineering unavailable. It is incomplete because every instrument we have ever pointed outward has been pointed from within the same plane, along the same range of directions, through the same foreground of disk material that our location imposes. The boundary of our bubble has never been mapped from a direction perpendicular to the disk. The full shape has never been seen. The polar vantage that would allow the complete picture to be assembled has been visited only briefly by 2 missions, neither of which was designed or positioned to make that measurement. What it would take to finally fill that gap, to approach the problem from a direction that no prior mission has attempted, is the question the next part of tonight addresses. The answer is more achievable than the delta V wall might suggest. It requires only the willingness to fall toward the sun before attempting to climb away from it. There is a way out of the plane that does not require 30 kilometers per second of brute force thrust delivered simultaneously from low Earth orbit. It does not require a rocket larger than any ever built. It does not require any technology that does not already exist, any physics that has not already been demonstrated, or any engineering principle that has not already been applied, in one form or another, on missions already flown. It requires instead a particular kind of patience and a willingness to fall before climbing. The principle at the heart of this approach is one of the most quietly beautiful ideas in all of orbital mechanics. It is counterintuitive only on first encounter. Once understood, it carries the clean inevitability of something that could not have been otherwise, a geometric truth that was always there, waiting to be noticed. A spacecraft that fires its engine deep inside a gravitational well, close to a massive body, moving very fast, extracts more useful energy from the same burn than it would if it fired the identical engine at the same thrust for the same duration in open space, far from any gravitating body. The fuel does the same chemical work. The engine produces the same thrust. The burn lasts the same number of seconds. But the energy delivered to the spacecraft's orbit is dramatically larger when the burn happens at high velocity near the bottom of a gravitational well than when it happens at low velocity, far from any source of gravity. The reason is that kinetic energy, the energy of motion, scales not with velocity, but with the square of velocity. Doubling the speed of an object quadruples its kinetic energy. Tripling the speed multiplies the energy by 9. The relationship is not linear. It curves upwards steeply as velocity increases. When a spacecraft burns its engine, it adds a fixed change in velocity, the same delta V, regardless of where the burn occurs. But the change in kinetic energy produced by that fixed velocity increment depends on how fast the spacecraft is already moving when the burn happens. A spacecraft moving at 100 kilometers per second gains far more kinetic energy from a burn that adds 1 kilometer per second than a spacecraft moving at 10 kilometers per second gains from the identical burn. Near the bottom of a deep gravitational well, objects move fast. Near the Sun, the deepest gravitational well in the solar system, they move very fast indeed. A spacecraft falling inward from Earth's orbit accelerates continuously as it descends, reaching speeds well in excess of 100 kilometers per second at the closest approach to the Sun. At those speeds, the squaring relationship that governs kinetic energy means that even a modest burn, modest in terms of the delta V it produces, delivers an enormous change in the spacecraft's total orbital energy. The principle has a name. It is called the Oberth effect, after an early pioneer of rocket theory whose foundational work on the mathematics of spaceflight helped establish the field in the decades before any rocket had left the atmosphere. The Oberth effect is not a trick or an approximation. It is an exact consequence of the relationship between kinetic energy and velocity applied to the specific situation of a rocket burn performed at high speed near a gravitating body. Every experienced mission designer understands it intuitively. Every efficient interplanetary trajectory makes use of it, at least implicitly. When a spacecraft departing Earth fires its engine to escape Earth's gravity and begin its journey toward another planet, the burn is performed at the lowest point of the Earth orbit, the closest approach to Earth, because that is where the spacecraft is moving fastest and where the burn does the most useful work. When a spacecraft arriving at a destination planet wants to slow down and enter orbit, the braking burn is performed at the closest approach to that planet for exactly the same reason. The Oberth effect is the standard wisdom of how to spend propellant efficiently around any gravitating body. Apply the principle to the Sun, the deepest gravitational well available anywhere in the solar system, and the result is one of the most powerful and most elegant maneuvers in the entire catalogue of proposed spaceflight. Architecture. Picture the trajectory in its simplest form. A spacecraft departs Earth and turns inward, beginning to fall toward the Sun. No fuel is burned during the fall itself. The Sun's gravity provides the inward acceleration entirely for free, pulling the spacecraft downward and forward along a tightening curve toward the closest approach point. As the spacecraft descends, it accelerates continuously. The Sun grows in the forward field of view larger than it has appeared from any point where a spacecraft has ever previously traveled. The heat shield brightens on its sun-facing side as the intensity of solar radiation increases with the inverse square of the decreasing distance. At perihelion, the closest point of the approach, the moment of maximum speed and maximum solar intensity, the deepest point of the gravitational descent the engine fires. The burn is brief, perhaps a few minutes, perhaps less, depending on the architecture. The spacecraft is moving so fast, and the Oberth amplification is so favorable that only a short burst of thrust is needed to redirect the trajectory dramatically. The delta V of the burn itself may be only a few kilometers per second, but because of where and when that burn occurs, the change in orbital energy it produces is equivalent to what a much larger burn would have delivered from Earth orbit. After the burn, the spacecraft swings back outward, but now it is rising along a path that no direct ascent from Earth could ever have produced. The trajectory carries it out of the plane, climbing steeply toward the solar polar regions on an orbit that the Oberth effect has made affordable, that brute force alone could never have reached. The savings are not marginal. A trajectory to a polar solar orbit that would cost approximately 30 kilometers per second of delta V, delivered as direct perpendicular thrust from low Earth orbit, can be achieved through a well-designed perihelion burn for perhaps 3 or 4 kilometers per second applied at the right moment near the Sun. The reduction is not by a few percent, it is by nearly an order of magnitude. The same mission that was completely impossible with available chemical rockets becomes achievable provided the spacecraft can survive the thermal environment at perihelion long enough to perform the burn. The thermal challenge is real, it is also solved. Near the closest approach to the Sun that the most aggressive perihelion burn architectures require, the intensity of solar radiation is tens or even hundreds of times greater than what a spacecraft experiences at Earth's distance. The temperature on the sun-facing side of an unprotected structure would rise rapidly to levels capable of melting or damaging conventional materials. Sensitive optical instruments, electronic components, and structural elements that would function perfectly at Earth's orbital distance would fail quickly in this environment without protection. The solution is a heat shield, a specially designed barrier positioned between the Sun and the spacecraft body, blocking the direct solar radiation and maintaining the spacecraft's components at survivable temperatures by absorbing, reflecting, and radiating the thermal load. Heat shields of this kind are not theoretical constructs. They have been built and flown. A recent mission to the inner solar system, specifically designed to study the Sun's corona and the solar wind near its source, has approached the Sun to within a small fraction of Mercury's orbital distance. Surviving repeated close perihelion passes behind a carbon composite heat shield whose sun-facing surface reaches temperatures sufficient to glow faintly orange-white, while the spacecraft instruments just centimeters behind it operate at nearly room temperature. The engineering exists. It has been demonstrated in the most demanding thermal environment available within the solar system. The perihelion burn architecture is not waiting on a thermal solution. The thermal solution is already flying on another mission. The remaining constraint is propellant management. The Oberth effect delivers its maximum benefit only when the burn is performed at the moment of closest approach, the single instant of maximum speed. Any propellant consumed before that moment does not benefit from the deep well amplification. The most efficient version of the architecture, therefore, saves virtually all of the spacecraft's propellant for the perihelion burn itself, spending as little as possible on any earlier maneuver. The inward fall from Earth's orbit is accomplished without any thrust at all, using the Sun's gravity alone to provide the acceleration. The spacecraft arrives at perihelion with a nearly full propellant load, burns briefly and decisively at the moment of maximum leverage, and departs on the new high-inclination trajectory. The elegance of the architecture is that the most expensive thing the mission needs to accomplish the change of trajectory from the disk plane to a polar orbit is purchased almost entirely with the Sun's own gravitational energy, amplified through the squaring relationship of kinetic energy, rather than with the spacecraft's limited propellant supply. The Sun itself provides the leverage. The spacecraft provides only the timing and the direction. There is a second path out of the plane, and it carries no propellant at all. A solar sail is an extraordinarily thin, highly reflective surface, measured not in meters, but in thousands of square meters, thinner than a human hair, deployed in space from a compact stowed configuration using lightweight booms or inflation mechanisms. When sunlight strikes the sail and reflects away, each photon transfers a tiny amount of momentum to the sail surface. The force from any single photon is unimaginably small, far below what any instrument sensitive enough to detect it could physically measure in isolation. But integrated across thousands of square meters of sail surface, integrated across hours and days and months of continuous sunlight, the cumulative momentum transfer becomes meaningful. The sail accelerates, slowly but continuously, and without consuming any propellant whatsoever. A sailcraft can maneuver by tilting the sail relative to the Sun, orienting its surface at different angles to choose whether the resulting thrust adds energy to the orbit, removes it, or redirects it sideways. By carefully controlling the sail angle throughout each orbit, the spacecraft can spiral inward or outward, change its orbital inclination, adjust its orbital period, or combine these effects to navigate toward a desired destination. The available thrust directions are constrained by the requirement that the sail must face generally toward the Sun to receive sunlight, but within those constraints, a skillful trajectory design can accomplish a wide variety of orbital changes given sufficient time. The fundamental advantage of solar sailing for out-of-plane missions is not that it is fast. It is not fast. The thrust is small, and accumulating the orbital changes needed to reach high solar latitudes takes years rather than months. The advantage is that it does not run out. As long as the Sun shines, and the Sun will shine for another 5 billion years, the sail has thrust. Mission lifetime is limited by the durability of the sail material and the operational lifespan of the spacecraft's electronics, not by the consumption of any finite propellant supply. A sailcraft approaching the Sun for a polar mission could spiral inward continuously, gaining both speed and altitude above the plane with each revolution, climbing steadily toward the polar vantage without ever exhausting the resource that drives it. The technology has been demonstrated. Small experimental sailcraft have been deployed and operated in Earth orbit and in interplanetary space. The deployment mechanisms work. The attitude control systems work. The physics works exactly as predicted. What has not been built is a sail large enough, and combined with a spacecraft capable enough to perform the kind of sustained interplanetary maneuvering that a serious polar solar mission would require. That gap is not a physics gap. It is a funding and priority gap. The engineering path from demonstrated small-scale sailing to a full interplanetary sailcraft is well understood. It has not been walked because the resources to walk it have not been committed. The most promising architectures studied in detail over recent decades combine the two approaches, using each where it offers the greatest advantage and handing off between them at the moment when the transition delivers the largest benefit. A sailcraft is deployed from Earth and uses continuous sunlight pressure to spiral inward toward the Sun without burning any propellant. The inward spiral takes time, perhaps a year or two, but it costs nothing in fuel. As the sailcraft descends toward the inner solar system, it accelerates, the solar radiation intensity increases, and the available sail thrust grows because the same sail area intercepts more photons per second at shorter distances from the Sun. The combination of increasing speed and increasing thrust makes the inward spiral progressively faster as it proceeds. As the sailcraft approaches the perihelion distance, where the O-berth effect becomes maximally favorable, the sail is either folded, furled, or jettisoned, removed from the configuration before the thermal environment becomes severe enough to damage it. A compact, high-energy chemical stage that has been carried along for this purpose fires at the moment of closest approach, delivering the perihelion burn that throws the spacecraft out of the plane on a steep polar trajectory. The combined architecture trades engineering complexity, 2 propulsion systems, 2 thermal regimes, a carefully managed transition between them for a dramatic reduction in the total mission cost compared to either approach used in isolation. The sail handles the patient, efficient work of reaching perihelion without spending propellant. The chemical stage handles the brief, decisive work of the perihelion burn itself. Neither could accomplish the full mission alone within practical constraints. Together, they create a mission profile that the available technology can actually execute. Variants of this combined architecture have been studied, modeled, refined, proposed, and set aside repeatedly over the past several decades. Mission concepts have been worked out in considerable engineering detailed trajectory analyses, thermal models, mass budgets, instrument complement studies, communication system designs. The work is real and substantive. None of it has yet been assembled into a flight mission. Other propulsion approaches could support out-of-plane solar missions given adequate development investment. Ion engines, which use electrical power to accelerate ionized propellant to exhaust velocities many times higher than chemical rockets can achieve, have already demonstrated their utility on several interplanetary missions, performing trajectory maneuvers that chemical propulsion could not have afforded. An ion-propelled spacecraft, given sufficient electrical power and sufficient operational time, could accumulate the inclination changes needed to climb out of the plane through continuous low-thrust maneuvering. No planetary flyby required, no perihelion burn required. Simply the patient accumulation of small velocity changes over months and years of continuous thrusting. The limitation of ion propulsion in the inner solar system is power. Ion engines require substantial electrical power to operate at useful thrust levels. In solar panels, the most practical power source for inner solar system missions, provide ample power at Earth's orbital distance and inward. A solar-powered ion-drive spacecraft spiraling out of the ecliptic toward the Sun's poles would have access to increasing solar power as it descended toward the inner system, making the ion propulsion more effective precisely where the mission requires it most. Nuclear electric propulsion, a nuclear reactor providing the electricity for high-efficiency ion thrusters, could in principle provide even greater capability. A nuclear power source delivers far more electricity than solar panels of any practical size, and it does so regardless of distance from the Sun, making it effective in the outer solar system as well as the inner. A nuclear electric spacecraft could climb out of the plane, position itself above a solar pole, observe for years, and continue maneuvering throughout the mission without the power constraints that limit solar electric systems. The technology has been studied. It has not been flown at the scale that such a mission would require. The point toward which all of these architectures converge is the same point. The plane is not a permanent barrier. The geometry of the solar system does not make the vertical axis inaccessible. It makes it expensive in propellant if approached directly, and far more affordable if approached cleverly. Every technique described here, the Jupiter flyby, the Venus gravity assist sequence, the perihelion burn, the solar sail, the combined sail and burn architecture. The ion drive represents a different way of working with the gravitational and energetic landscape of the solar system rather than against it. The landscape is not hostile, it is simply structured. It rewards patience and penalizes impatience. It rewards missions that fall before climbing, that borrow from planets before departing from them, that store the Sun's own gravitational energy through the mechanics of deep well burns, rather than paying for every meter of altitude with propellant carried from the launch pad. The missions that have traveled furthest and accomplished most in the history of solar system exploration have been, without exception, missions that understood this, that worked with the structure of the gravitational landscape rather than ignoring it. A mission to the polar regions of the Sun that followed the same philosophy that used the Sun's own gravity to amplify the effect of a modest burn, that borrowed patience from the sail before demanding precision from the rocket, would be not merely possible but achievable with technology already demonstrated, with engineering already understood, with trajectories already calculated. What it requires is not a new discovery. It requires a decision. The deep well of the Sun is not only the obstacle that has kept the polar vantage empty for so long, it is also the lever that can finally place an instrument there. Used at the right moment, in the right direction, with the right preparation, the Sun's own gravity can deliver a spacecraft to the most consequential, unreached vantage point in the local solar system. The lever has been known for decades. No one has yet chosen to pull it. Suppose, for the length of tonight's final part, that the mission has been flown. Suppose the architecture was chosen, the engineering was completed, the spacecraft was assembled and tested and launched. Suppose the sail deployed cleanly in the weeks after departure, caught the sunlight, and began the patient inward spiral. Suppose the perihelion burn executed precisely at the moment of closest approach, the engine firing briefly and decisively in the deepest available gravitational well, the trajectory bending sharply out of the plane exactly as the calculations predicted. Suppose the spacecraft climbed outward from that burning moment on a new orbit, steep, inclined, rising above the disk of the solar system on a path that no prior mission had ever followed. Suppose it arrived. The instruments are functioning, the communications link is stable, the heat shield has done its work, and the spacecraft has survived everything the inner solar system could place in its path. The orbit is settled. The polar vantage, empty for the entire history of spaceflight, now holds a single instrument platform, turning slowly, its sensors pointed in every direction simultaneously, observing a version of the solar system that no human instrument has ever recorded. What would it find? The first change is the sky itself. From inside the ecliptic, the night sky carries a faint but pervasive contamination. The zodiacal cloud, the diffuse sheet of dust that hugs the plane of the planets, replenished continuously by asteroid collisions and cometary shedding, scatters sunlight back toward any observer within the plane. The glow is gentle, it is not overwhelming, but it is everywhere along the ecliptic, and it raises the background brightness of the sky in the directions where the most interesting solar system objects happen to lie. Sensitive instruments searching for faint signals, the reflected light of a distant exoplanet's atmosphere, the microwave imprint of the early universe's first moments, the soft infrared glow of a distant brown dwarf companion, must work against this background, extracting their targets from the scattered light of the disk that surrounds the observer. From above the plane, that background retreats. The zodiacal cloud lies below and behind the spacecraft, its scattering geometry no longer directed upward through the field of view. The sky above the polar vantage would be cleaner than any sky available from anywhere within the inner solar system. Not perfectly clean, there is always some residual dust, some scattering, some foreground emission from various sources, but measurably, significantly cleaner than the sky seen from any in-plane position. For observational astronomy, the implications are real and practical. Telescopes searching for biosignatures in the atmospheres of distant exoplanets, searching for the specific chemical imbalances that might indicate biological processes operating on a remote world, are limited in their sensitivity by the zodiacal foreground. The glow of the disk raises the noise floor, against which the faint spectral features of a distant planetary atmosphere must be detected. A telescope operating from the polar vantage, looking outward through the cleanest available window in the inner solar system, would reach fainter signals with shorter integration times, or reach the same signals with smaller aperture, a difference that translates directly into mission cost and scientific reach. Measurements of the cosmic microwave background, the faint thermal radiation that fills the universe, the relic of the moment when the early universe cooled enough for neutral hydrogen atoms to form and radiation to travel freely for the first time, are similarly affected by foreground emission from solar system dust. The microwave background carries in its tiny temperature variations, fluctuations of a few parts in 100,000, the imprint of quantum density perturbations in the earliest moments of cosmic history, the seeds of every galaxy and cluster of galaxies that subsequently formed. Mapping those temperature variations with the greatest possible precision is one of the central projects of contemporary cosmology. The zodiacal foreground is one of the foreground components that must be subtracted from the microwave sky maps before the cosmological signal can be cleanly extracted. From a polar vantage, a significant fraction of that foreground would simply be absent. The polar sky, in other words, is not merely a good place to study the sun. It is a uniquely clean platform for nearly every kind of astronomy that depends on detecting faint signals against an unwanted background. The darkness is an instrument in itself. The local environment immediately surrounding the spacecraft would also be different from anything measured within the plane. Inside the ecliptic, a spacecraft sits within the slow, variable, turbulent solar wind of the streamer belt, the equatorial plasma environment shaped by the complex magnetic structure of the closed-loop corona, varying in density and direction from hour to hour as the sun rotates and presents different regions toward the spacecraft. Crossings of the heliospheric current sheet bring reversals of the local field direction. Interactions between fast and slow wind streams produce compression fronts and turbulent boundaries. The equatorial solar wind is not a steady flow. It is a dynamic, structured, continuously changing environment. As the polar spacecraft climbs to higher solar latitudes, the wind surrounding it changes character. The slow equatorial wind gives way gradually to the fast polar wind streaming outward from the polar coronal holes, smoother, more uniform, less turbulent, carrying the clean, open field line signature of its origin in the high-latitude corona. The transition between the two wind regimes is not abrupt. It unfolds across a range of latitudes, with mixed regions where fast and slow winds interact and boundaries between the two stream types produce their own localized structures. The transition zones were mapped at limited resolution by the first polar mission. A sustained polar spacecraft operating continuously through the transition and beyond would characterize those boundaries with a precision not previously available, tracking how the transition latitude changes with the solar cycle, how it shifts as the polar coronal holes expand and contract, how the fast wind's properties vary with the solar activity level at the time of observation. Above the transition, in the clean, fast wind streaming outward from the polar hole, the spacecraft would operate in the solar wind environment, least disturbed by the complex structures of equatorial activity. Magnetic field measurements in this region would test directly the surprising large-scale field uniformity that the first polar mission suggested. The tendency of the radial field component to become roughly latitude-independent at large distances from the sun. Smoothed by the way the solar wind carries magnetic flux outward across the heliosphere. A sustained measurement baseline across years of operation would establish precisely how this uniformity arises, how it evolves through the solar cycle, and how it depends on the state of the polar coronal holes from which the fast wind originates. Turning the spacecraft's instruments downward toward the plane of the planets lying below and spread out in every direction from the vantage of the polar orbit would produce something that has never existed in the entire history of astronomy. A plan view image of the solar system. From Earth, and from every spacecraft ever operated within the ecliptic, the solar system is seen edge-on. The planets appear strung along a single line across the sky, the ecliptic, because the observer is embedded in the same plane the planets occupy. The disk is invisible as a disk from inside itself. Its geometry can be inferred, can be calculated, can be modeled with extraordinary precision, but it cannot be seen. It cannot be photographed. No image taken from any position within the plane can show the plane as the flat, organized, geometrically coherent structure that it actually is. From above the plane, the entire inner solar system would lie below the spacecraft in a single field of view. Earth and the inner planets would appear as small bright points, each moving slowly along its orbit, the familiar spacing between the planetary orbits visible at a glance for the first time. The relative sizes of the orbits, the slight eccentricities that bring each planet closer to or farther from the Sun at different points in its year, the gentle mutual inclinations that cause each orbit to sit at a fractionally different angle from the others, all of this structure, normally inferred from centuries of careful measurement, would be directly visible in a single image. The asteroid belt, the broad ring of rocky bodies orbiting between Mars and Jupiter, would appear as a faint, diffuse band, slightly above and below the plane in places, but settled predominantly into a thin sheet between the two planets. The gaps in the asteroid distribution carved by gravitational resonances with Jupiter, the Kirkwood gaps, named for the 19th century astronomer who first identified them in the orbital period. Statistics of known asteroids would be visible as slightly darker bands within the belt's glow. The Trojan asteroids sharing Jupiter's orbit, the Greek camp leading Jupiter, and the Trojan camp trailing it, would appear as two distinct concentrations flanking the giant planet along its orbital path. The zodiacal dust cloud, seen from above rather than from within, would appear as a flat, bright disk surrounding the Sun denser in the inner regions, thinning gradually outward, its flat geometry unmistakable, from a perspective that the geometry itself had always hidden from any observer within it. This image does not exist. It has never been taken. It cannot be taken from anywhere within the plane because the plane's own geometry prevents it. No mosaic of images from spacecraft distributed across the ecliptic, no clever reconstruction from in-plane observations, no computational model, however precise, is a substitute for direct observation from above. The plan view portrait of the inner solar system, the view that would show, at a glance, the organized flat disk of orbiting matter that has surrounded the Sun for 4.5 billion years, is one of the great unfinished images of the space age. It is waiting for a spacecraft that has not yet been built. Further out, beyond the planetary disk and into the outer heliosphere, the polar spacecraft's measurements would begin to address the open question that no in-plane observation can resolve. As the orbit carries the spacecraft progressively further from the Sun along its inclined path, or as a separate outward-bound mission climbs out of the disk on a high-latitude trajectory, it would pass the regions of the outer heliosphere, where the two competing models of the heliosphere's shape make different predictions. The comet model and the croissant model agree reasonably well in the upwind direction, where the only existing boundary measurements were made. They disagree significantly in the polar and downwind directions. The magnetic field structure at high heliospheric latitudes, the plasma density distribution, the character of the energetic neutral atom flux arriving from the boundary, all of these differ between the two models in the polar region in ways that in-situ measurements could discriminate clearly. A spacecraft traversing the high-latitude heliosphere would return data that pointed definitively toward one model or the other, or toward a configuration neither had imagined. If the spacecraft eventually crossed the heliopause in the polar direction, descending across the boundary from above, entering the local interstellar medium in a direction perpendicular to the disk, it would return the first boundary measurement ever made outside the plane. The first data point on the surface of our bubble from a direction that no prior mission had approached. The crossing distance, the field reversal, the plasma transition all would be recorded for the first time from a direction that constitutes most of the bubble's surface area, yet has never been sampled. The shape of our home would finally begin to have an outline drawn from direct observation rather than from inference and competing theoretical models. Looking further still outward past the heliosphere into the galactic sky beyond the polar vantage would present a view geometrically unlike anything familiar from Earth or from any in-plane spacecraft. The band of the Milky Way, tilted by roughly 60 degrees relative to the ecliptic, would appear in a dramatically different orientation than the one visible from the planet's surface. The familiar horizontal river of light, crossing from horizon to horizon in the terrestrial night sky, would instead rise steeply, a great inclined band, cutting across the sky at an angle that would immediately signal to any observer that this vantage point was profoundly different from anything on or near Earth. The bright concentration of the galactic center, visible from Earth's surface in the direction of Sagittarius, would lie in a different position relative to the Sun than it does from within the plane. The dark dust lanes threading through the stellar light, the soft brightness of the inner spiral structure, the distant faint smudges of neighboring galaxies, all would appear in an arrangement that no human eye has ever seen and no camera has ever recorded. The direction below the Sun's south pole, in galactic terms, opens into a region of the local bubble, with relatively low foreground obscuration, a direction where the interstellar gas and dust between the Sun and the wider galaxy are somewhat thinner than average, providing a marginally cleaner sightline out into the universe beyond. A telescope pointed in this direction from a polar solar vantage would look through the local bubble toward the general field galaxy population with a foreground contamination somewhat lower than most other directions offer. For surveys of the distant universe, for studies of the faint galaxy population at large redshift, for measurements of the large-scale structure of the cosmic web, the polar south direction in galactic coordinates is among the more favorable windows available. The cosmic microwave background measured from this vantage would be cleaner in a different sense as well. The solar system contribution to microwave foreground emission from the zodiacal dust, from the outer dust in the Kuiper belt, from various resonant structures in the disk, would be dramatically reduced for an observer above the plane. The galactic foreground, the dominant contaminant in precision microwave background measurements, would be no different from what any other vantage observes, but the solar system foreground would be significantly less. For the next generation of cosmological experiments seeking to measure the polarization of the microwave background at the highest available precision probing for the faint imprint of primordial gravitational waves generated in the first fraction of a second after the universe began, every reduction in foreground contamination translates directly into scientific reach. The polar solar vantage is not a specialized platform for solar physics that happens to have some secondary astronomical uses. It is a genuinely privileged observational position for nearly every kind of astronomy that cares about the faintest available signals. And beneath all of it, beneath the clean sky, beneath the plan view portrait of the disk, beneath the direct measurement of the heliospheric boundary, beneath the inclined galactic view, the spacecraft would look down at the Sun itself from the direction that matters most for understanding it. The polar surface would be visible as it has never been visible before. Not foreshortened, not compressed into a narrow strip along the limb of the equatorial disk, but seen from above, at an angle that resolves the actual structure of the polar region, the fine network of small magnetic concentrations woven through the granular surface, the dark expanse of the polar coronal hole spreading outward from the rotation axis, the individual polar plumes rising from the hole's interior in their slow radiating pattern, the boundary of the hole wandering irregularly across the high latitudes with its bays and peninsulas of open magnetic territory. The polar magnetic field, mapped continuously by the spacecraft's magnetograph across the full visible polar disk, he would produce the first long baseline measurement of how the polar field accumulates and reverses through the solar cycle observed from a geometry that removes the foreshortening that has limited every prior polar field. Measurement made from within the ecliptic, the approach of the magnetic polarity reversal, the poleward drift of the new polarity flux, the cancellation of the old polar field, and the establishment of the reversed one, all of this could be tracked in real time from above, watching the reversal unfold from the vantage that makes its mechanism most legible. The fast solar wind streaming outward from the polar coronal hole, measured simultaneously by in situ instruments in the spacecraft's local environment, and by remote imaging instruments observing its origin at the polar surface, would be studied as a connected system for the first time, linking the source conditions at the surface to the wind properties measured a short distance above, closing a causal chain that in-plane observation could never fully close because it was always observing the source and the wind from different geometric perspectives simultaneously. The polar sun, studied across years of continuous observation from a fixed polar vantage, would gradually yield the answers to questions that have been accumulating since the first photographs of the corona were taken during total solar eclipses in the 19th century. How does the polar field accumulate its strength across the years of each cycle? What drives the irregular migration of the coronal hole boundaries? What is the fine structure of the polar plumes? And how does it change as the surrounding coronal hole expands and contracts? How does the polar corona transition from the organized open field geometry of the hole's interior to the more complex structure at its boundaries? None of these questions can be answered adequately from the equatorial vantage. The geometry does not permit it. The polar view is required. There is no photograph of the solar system in plan view. There is no image of the sun taken from directly above one of its poles at full resolution, in stable conditions, maintained long enough to track the dynamics of the polar surface through a full solar rotation. There is no direct measurement of the heliospheric boundary in the polar direction. There is no long baseline record of how the polar magnetic field evolves through a complete solar cycle, observed from a geometry that actually resolves the polar structure without foreshortening. None of these things exist, not because the universe withholds them, not because the distances are prohibitive or the physics is unknown. They do not exist because the mission to collect them has not been built. The engineering is understood. The trajectories have been calculated. The scientific case has been made in technical detail across decades of peer-reviewed literature and mission concept studies and instrument development programs. The vantage is empty because no one has yet chosen to fill it. The solar system has held its shape for 4.5 billion years. The disk formed when the protoplanetary cloud collapsed, flattened by the rotation it could not shed, and assembled its planets in the plane it had defined. The planets have orbited in that plane ever since, carrying along every spacecraft launched from every one of them, every probe aimed at every destination, every instrument ever pointed outward from the thin inhabited layer of the disk's surface. The flatness is not an accident. It is not an obstacle. It is the natural consequence of physics, working patiently through the available material across timescales longer than anything biological can directly comprehend. The disk is the outcome. The orbital motion every spacecraft inherits is the disk's signature, written into every trajectory flown. The current sheet, the zodiacal glow, the twin solar poles, the shape of the heliospheric bubble, all of it is the geometry of where you are, seen from the one direction that the geometry itself has always made hardest to occupy. The view from above the plane would not change what the solar system is. It would not alter the physics of the polar wind, or the dynamics of the coronal hole, or the mechanism of the magnetic reversal. The universe does not require observation to continue operating. The process is run regardless of whether anyone is watching from the directions that would make them most legible. The photograph is for us. It is for the accumulated record of human understanding, the slow, patient, multi-generational project of building a complete picture of where we are and how the system we live inside actually works. Every image added to that record changes something about how the whole picture is understood. The plan view portrait of the inner solar system would change it in a way that no other single image could, showing, for the first time, the organized flat disk that has been inferred and modeled and described for centuries, rendered as a direct observation rather than a reconstruction. The portrait of our home has been assembled piece by piece across the 4 centuries since the first telescopes were turned upward. It is nearly complete in some directions. It is missing entirely in others. The polar directions above and below the disk, along the vertical axis that gravity locked everything away from 4.5 billion years ago, are the directions where the portrait is most incomplete and where the most consequential missing pieces remain. The sun turns slowly at the still center of the disk. It has been turning since before any solid body existed in the solar system. It will continue turning long after every spacecraft ever launched has either fallen silent or fallen inward and been consumed. The polar coronal holes expand and contract with the rhythm of the cycle. The fast wind streams outward from them in long, clean rays. The heliospheric current sheet ripples away from the equator in its slow ballerina geometry. The magnetic flux drifts poleward through the years of each cycle, accumulates at the poles, cancels and reverses, and begins drifting again. The bubble of the heliosphere breathes with the solar rhythm, pressing outward at maximum and retreating at minimum, its exact shape still uncertain in the polar directions for the simple reason that no measurement has yet been made there. All of this has been happening since long before any eye existed anywhere in the solar system to observe it. All of it will continue happening long after tonight. The architecture for the missing observation exists. The trajectories exist. The instruments exist. The physics has been understood for decades, and the engineering has been demonstrated in components across multiple missions. What does not yet exist is the assembled vehicle sitting above the plane, transmitting data from the empty vantage, filling the last major gap in the local map. That gap is patient. It has been patient since the first solar physicist looked at a photograph of the corona and wondered what the polar regions looked like from a direction the equatorial plane would never provide. It will remain patient for as long as it takes. The sun does not need the photograph. It has no use for our understanding of it. The processes that govern its behavior are indifferent to whether they are observed or unobserved, mapped or unmapped, understood or merely inferred. But the photograph is extraordinary because we need it, because the complete picture of where we are has always been worth the effort required to assemble it. Because the history of every image ever added to the record of the solar system, from the first telescopic drawings of sunspots in the early 17th century to the first close images of Pluto's surface retrieved a decade ago, has been a history of effort rewarded, of the unknown rendered known, to the inferred rendered directly observed. The vertical axis of the solar system is the last major direction from which the local record is essentially empty. The engineering to fill it is available. The science that would follow is substantial and irreplaceable. The portrait of our home is waiting to be finished. It will be finished when someone decides to finish it. Until then, the sun rests where it has always rested, at the still, burning center of the disk, turning on its axis at the pace its differential rotation has maintained across billions of years. The planets continue their quiet orbits in the plane they were born in. The polar wind streams outward from the coronal holes in long, clean rays that no instrument is currently positioned to measure from above. The heliospheric bubble holds whatever shape it actually holds, pressing against the surrounding interstellar medium in the polar directions where no crossing has yet been recorded. The sky above the sun's north pole is empty tonight. The sky below its south pole is empty as well. The missing spacecraft has not yet arrived. The missing photograph has not yet been taken. The missing data has not yet been transmitted across the distance between that unreached vantage and the receivers waiting for it here. None of this requires anything of you tonight. The gap in the portrait does not demand urgency. The universe is not impatient. The disk has held its shape for 4.5 billion years, and it will hold it for billions more. The polar vantage will remain available for as long as the sun burns, which is to say, for longer than anything we might plan for it. Let your breathing slow now. Let the long, quiet plane of the solar system settle around you as it always has. Let the directions above and below the sun remain where they have always been, patient, unhurried, holding in their emptiness the promise of the observations that will one day be made from them. The flatness continues. The planets continue their orbits. The polar wind continues its long outward flow along the open field lines, streaming away from the sun in long, clean rays into the heliosphere and beyond. The portrait is unfinished. It will be finished, and until it is, the empty vantage waits not as a loss, but as a promise, patient as the disk that surrounds it, quiet as the space between the stars, holding open the direction that has always been there and has never yet been filled.